Okay, let's jump right into this explainer. Right now, literally this very second, there's a highly complex, honestly kind of adorable, microscopic tug of war happening inside your body. We're talking about the delicate, life-saving balancing act of fluids, electrolytes, and acid-base chemistry that keeps you functioning every day. We've broken this explainer down into 5 neat sections. We're going to cover fluid balance and imbalances, push and pull pressures, edema and dehydration, the essential electrolytes, and finally acid-base imbalances explained. Let's get right to it. Section 1. Fluid balance and imbalances. Let's start by looking at homeostasis and what actually happens when our body's water levels get a little too high or a little too low. So let's look at the first major imbalance, hypovolemia. Simply put, when we're lacking the water we desperately need, we experience hypovolemia. You probably know this best as good old-fashioned dehydration. But here's the thing, when this happens, your body doesn't just sit around and do nothing. It triggers this massive systemic defensive response to save every single drop of water it possibly can. Now, on the flip side, holding on to way too much water gives us hypervolemia. This completely overloads the system. It dramatically increases internal pressure, putting immense strain on your vital organs. It's literally acting like an overfilled water balloon right before it bursts. And then there's the third scenario, which I think is absolutely fascinating, maldistribution. Sometimes the total amount of fluid you have is perfectly fine, but it gets lost in the wrong neighborhood. It leaks out and gets trapped in the interstitial space, entirely missing the blood vessels and cells where it actually belongs. Moving right along to Section 2, push and pull pressures. Let's see how all of this builds into an invisible pushing and pulling contest. This illustrates the exact competing forces at play here. On one side, we've got hydrostatic pressure. Think of this as the physical pushing force that shoves water out of your blood vessels. And on the opposing side is osmotic pressure, which is powered by solutes and proteins, desperately pulling that fluid back in. It's basically a continuous, microscopic arm wrestling match happening across every single cell membrane in your body. But what happens when a vital organ breaks down? Well, if your kidneys are damaged, they act like a broken filter. Instead of keeping the good stuff in, they let precious pulling proteins leak right out into your urine, a condition called proteinuria. Because those proteins act like tiny magnets responsible for that osmotic pull, losing them means your blood loses its pulling power entirely. The result? Fluid escapes out into the tissues, leading to massive swelling or edema. A classic real-world example of this is a patient suffering from severe liver disease, like cirrhosis. Your liver is essentially a biological factory for albumin, which is your blood's main pulling protein. If that liver factory shuts down and stops making albumin, you get a total loss of osmotic pull in the bloodstream. So gravity takes over, and all that fluid leaks massively directly into the abdominal cavity, causing a severe condition called ascites. That's ascites. Section 3. Edema and dehydration. Let's take a closer look at how our bodies react when these pressures completely break down. To really wrap our heads around the chemistry here, let's do a quick thought experiment. Imagine you have 2 cups. They have the exact same amount of salt sitting in them, but wildly varying amounts of water. Which one tastes saltier? Take a second and think about it. Naturally, that nearly empty cup is going to be incredibly salty, and this perfectly demonstrates how severe dehydration concentrates your blood sodium. It's a dangerous condition called hypernatremia. The medical suffix emia means in the blood, so hypernatremia literally translates to way too much sodium in the blood. Meanwhile, that second cup, the one overflowing with water, dilutes that exact same amount of salt. This beautifully illustrates hyponatremia during fluid overload. Taking this back into a clinical setting, if you've got too much fluid, just remember this rule. Excess fluid equals excess pressure. It acts just like a high-pressure hose inside you. This causes severe hypertension or high blood pressure and physically forces water straight into the lungs. We call this pulmonary edema, and you can actually hear crackles in the patient's chest when they breathe. Crazy, right? You'll also see severe swelling in the extremities, known as pitting edema. Now, to fight the opposite problem, dehydration, your body releases these incredibly clever hormones to quickly lock down your system. First, it senses the dangerous fluid loss and releases ADH, or antidiuretic hormone, to completely halt urination, a state called oligoria. It also triggers aldosterone, which essentially forces your body to hoard sodium. And because water always follows salt, retaining that sodium automatically pulls and retains every drop of water it can. This hormonal lockdown, by the way, is exactly why your urine turns that dark yellow color when you haven't been drinking enough water. Moving on to Section 4, the essential electrolytes. Let's zoom in even closer now to look at those tiny, sparkling minerals floating inside that fluid. The absolutely crucial point here is knowing exactly which primary organ each electrolyte targets. If your sodium levels are off, well, expect brain confusion or even nervous system issues. Potassium, that directly regulates your heart and cardiac rhythm, so an imbalance there is super dangerous. Calcium is the absolute boss of your bones and muscles, and magnesium, that directly impacts your reflexes and blood pressure. You know, I absolutely love this catchy little clinical rule. It helps you remember exactly how calcium works in the body. When calcium is away, muscles play. So let's break that down. Without enough calcium to lock down the muscle fibers, meaning when it's away, your muscles are going to spontaneously twitch and go into severe spasms, contracting uncontrollably. On the other hand, abnormally high calcium leads to excessive muscle relaxation. It just shuts the whole operation down. Finally, we've arrived at Section 5, Acid-Base Imbalances Explained. Let's decode the chemistry of your blood. To solve literally any acid-base puzzle in a clinical setting, you absolutely must memorize these two vital magic numbers. First, your blood's normal pH hovers tightly between 7.35 and 7.45. That incredibly narrow window really highlights just how delicate the human body actually is. Even a tiny shift outside that range can be life-threatening. And second, your normal carbon dioxide, or CO2, sits right between 35 and 45. Using those numbers, we can actually turn scary medical math into a simple, fun, 3-step minigame to instantly diagnose what's going wrong. Step 1. Look at the pH. If it's below 7.35, it's acidosis, and above 7.45 is alkalosis. Step 2. Look at the CO2. If it's abnormal, then your root cause is respiratory. Step 3. If CO2 is somehow normal, you look at the bicarbonate. If that's out of range, the issue is metabolic. Okay, let's test this out. Looking at patient A, their pH is low at 7.25, so it's acidosis. Their CO2 is abnormally high at 53, making it respiratory. Bam, respiratory acidosis. Now, patient B has a high pH of 7.55, meaning alkalosis. Their CO2 is totally normal at 37, but their bicarbonate is high at 30. Boom, metabolic alkalosis. It's that easy. It is just incredible to think about this delicate, beautiful chemistry keeping us alive every single second. Knowing about this microscopic tug of war happening inside you right now, how perfectly balanced are your body's fluids and electrolytes today? What happens when you throw in extreme diets, intense endurance sports, or daily medications? How hard does your body have to work to save you from yourself? Take a moment today to appreciate that invisible, perfect balance. Thanks so much for joining me on this explainer, and keep questioning the science inside you.